Hi guys, today we're going to be talking about numbers as ordered sets, and more importantly, ordinal numbers, but we'll get to that. So let's just jump right into it. Recall in the first video that there was this idea of a successor way to represent numbers. We defined 0 as 0, 1 as the successor of 0, 2 as the successor of the successor of 0, and so on, so that n would be the nth successor of 0. Now, when we want to interpret numbers as sets, we should keep two ideas in mind. The first is this idea of cardinality, which we developed in the second video. These sets, let's say, they should have the same cardinality as the number they represent. So, for example, 0, there's really only one choice for 0. That's the empty set, the set that contains nothing. The second thing is that we should want to keep these sets as simple as possible. We want to assume as least as possible. So when we try to define 1, we need a set that has one thing in it. We could define 1 as the set containing 0, that has one thing. How might we define 2? Well, what sets do we know exist? We know the empty set exists. We also know the set containing the empty set exists. So we could say that 2 is a set containing 0 and 1, which is, as a reminder, that's simply the empty set and the set containing the empty set. And in fact, whenever we do construct the next natural number, that'll just make a whole new set, which we could add in to get the next natural number. So in general, we represent n as the set containing 0, 1, and all the natural numbers up until n minus 1. So when we connect this idea back to successor functions, if we want to find the successor of some natural number n, all we have to do is copy all the elements that we had in n, but also add n to the set. So we take n union with the singleton set of n, and this will get us n plus 1. All we need to start with is 0 being the empty set and use this successor function over and over again, and we can get sets that have the same cardinality as the number they represent, and they're as simple as possible. In honor of its creator, these numbers are known as the von Neumann Ordinals. Now, the interesting about this is that these ordinals have certain special properties. The first of which that we should notice is that each natural number contains all the natural numbers that are less than it. For any natural number that is less than some natural number n, that's the same thing as saying it's an element of n. You could also say that x is a proper subset of n. And so we can see that exactly here. We can see that 1 is an element of 2, but 1 is also a subset of 2 since 2 contains 0, a proper subset. The idea here is that there's this equivalence between all these notations here. That's one thing that makes this representation of the natural number special. The great thing about this equivalence between less than, element of, and proper subset is that it gives us a way to order the sets. And when we order the set, there's a traditional graphical representation that we use to them, and it's called a matchstick representation. And so what we do is we take some natural number, like 4, and we could represent it as the set of its elements. So remember that 4 is a set containing 4 elements, 0, 1, 2, and 3. And we simply order the matchsticks according to this special equivalence. And we can do this for even larger numbers. I could consider representing 5 as a set of 5 elements like this, or 6 like that, or so on. We keep going on and on and on. And notice the special thing that happens when I do this. If I look at where 4 is, if I take all the matchsticks that come before 4, that forms the set which represents the natural number 4. So in a way, this 4 here, it determines an initial segment of matchsticks, which represents the set of 4. We can also define some arithmetic operations using these matchsticks. Another thing I should add is that when we order these sets with this less than or element of relationship and put them into a matchstick representation, we call these numbers ordinal numbers because they're ordered and they represent numbers. And we'll come to see exactly how that plays later. However, we can define some arithmetic operations for now. Let's define addition. So given two ordinal numbers, alpha and beta, we can add them together by concatenating the lines in order. So for example, if I want to add 2 and 3 together, this could be represented, I could use their matchstick representations. So I have 0 and 1 for 2, and then for 3, I have 3 matchsticks. And when I concatenate them together, I get 5 matchsticks. But when I put them in order, it's actually the set of matchsticks which represents the number 5. This is the initial segment determined by 5. So cool, we have addition. We can also do multiplication. So if I multiply two ordinal numbers, alpha and beta, I can do that by replacing each matchstick in beta with a new copy of alpha. So now if I do 2 times 3, that's the same as starting with 3 and replacing each of these matchsticks with a copy of 0 and 1. So now we have 6 matchsticks in order when we replace it. And that comes out to be the initial segment determined by 6. This is the set that represents the ordinal number 6. So perfect, we have multiplication. So like in the cardinal case, things are pretty boring when we consider only finite sets. So let's take a look at infinity. Again, this requires us to assume that infinity exists. But let's suppose it does. Let's suppose that there is an ordinal omega which consists of all of the natural numbers. In matchstick notation, that would look like this, where we simply just have an infinitely long sequence of matchsticks and they're labeled with the natural numbers. With this omega, we can still do ordinal operations. We can still do addition and multiplication. So for example, omega plus 1 is simply omega plus an extra 1. And so when we concatenate both of these in order, what we actually get is a whole different number, which starts being labeled 1, 2, 3, 4, 5, and so on. But the last matchstick is labeled omega. And if you think about it, this is actually consistent with our idea of successor functions. S of omega took the previous set and took it with the union of the set containing itself. And that is actually exactly what omega plus 1 is. Omega plus 1 is the set containing all elements of omega and omega itself. So plus 1 is actually equivalent to the successor function. Another cool thing about this is that omega plus 1 is actually bigger than omega. Why is that? Well, we saw from our definition earlier that omega is an element of omega plus 1. So by our special equivalence, we know that omega plus 1 has to be bigger than omega. Now, if this definition doesn't work for you, especially because it seems to be pretty set heavy, there is a much better graphical representation of what we've done here. How can we determine which ordinals are bigger? And it's done through pairing the elements in a 1-to-1 correspondence from left to right starting at 0 in order. What I mean by that is we start by pairing 0 with 0, 1 with 1, 2 with 2, 3 with 3, and so on. And we can see when we do this, we can pair all of the elements of omega. However, we will not be able to pair the last matchstick in omega plus 1, which is omega, because there is no last element in omega. It would just pair off with everything else. So what this is called is an order isomorphism. And essentially, this tells us the order that ordinal numbers should come in. If we have an order isomorphism, which uses up all the elements, then we know that those two ordinal numbers are equal to each other. However, if not all the elements of one of the ordinals is paired, then that ordinal is greater than the other one. So in this case, omega plus 1 is going to be greater than omega. All right, so here I have our matchstick representation once more. And what we can do is we can represent omega as the extra line because omega defines the initial segment, which contains all the elements in omega, and we can keep ordering it. So we found out that the successor of omega, omega plus 1, is larger than omega. So, and rightfully so, because it is represented by the matchstick that is right after omega plus 1. And we can actually keep going with this. We can create greater and greater ordinals by just keep taking the successor of the previous one. So we've created a whole new sequence of infinite ordinals. And we can keep going further. After the infinite sequence of successor ordinals, we can just draw an extra line and call it omega plus omega. And you can see exactly what omega plus omega looks like. Remember, each of these ordinals defines the initial segment, so omega plus omega is everything before it. So it's an infinite sequence and then omega followed by an infinite sequence. Omega plus omega is the same thing as omega times 2, and we can keep on going. We can get omega times 3, or even omega times 4, or even something like omega times omega, where we have an infinite series of infinite sequences with the infinite number of omegas between them. So why are we dealing with ordinal numbers? What do they give us? Sometimes induction is too short. And what I mean by that is normal induction, even strong or weak induction, whatever it is, normal induction it's usually like this. You prove some property for 0, and then you also prove that if you know the property holds for n, the property also holds for n plus 1. And this is great for most of the cases of induction that we come across in discrete math. We prove a case for 0, and then we prove a case for 1, and then for 2 and 3 and so on. But we actually hit a brick wall. If we ever have a sequence that goes past the natural numbers, say has an omega number, we'll never be able to reach that with this normal induction hypothesis. So what's the solution? It's transfinite induction. Induction that goes beyond the finite case. If you can prove some property holds for an ordinal number epsilon, for all epsilon in some other ordinal number alpha, then this will imply that the property holds for alpha. So this is simply a generalization of what was happening before. And so here's how transfinite induction picks up the slack. Regular induction says, 0 implies 1, implies 2, implies 3, implies 4, and so on. And it just keeps going on here, but it never reaches this omega. But transfinite induction bridges the gap. But when we come to these limits, and transfinite induction says, as long as you prove that the property holds for all of the ordinal numbers before omega, then this will imply that omega is actually proved. And omega plus 1, and omega plus 2, and so on. And all of these will get proved. And the initial segment determined by omega times 2 will also get proved, and so on. And so transfinite induction lets us go above and beyond. It's this idea that each ordinal number alpha determines an initial segment. So this is really useful whenever you are dealing with sequences, especially infinite sequences that can be ordered by ordinals. And as long as that sequence has a starting element, it can always be indexed by ordinal numbers. One special application for this is actually cardinality, and that's what we're going to talk about next. Cardinality deals with something that is completely different than ordinal numbers. Cardinality deals with the size of sets. Ordinality deals with sets that are ordered. However, cardinals they're not just the size of sets. Cardinals are actually defined in terms of ordinal numbers. And I'll show you what I mean. Here's the definition of cardinal numbers. The cardinality of a set is the smallest ordinal which that set forms a one-to-one correspondence with. So you can define cardinality as a set with the same size. So for example, let's find the cardinality of the set containing the letters A, B, and C. Obviously, this has cardinality 3, which is actually, by our definition, this is the smallest ordinal number the set ABC can form a one-to-one correspondence with. But let us also remind ourselves, what exactly is the number 3? The number 3 is the set containing the empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. Yeah. Right, which is also the set containing 0, 1, or 2, which we just use our matchstick representation to draw. We can also find the cardinality of the natural numbers. So the cardinality of the natural numbers, quite obviously, is omega. That's because we can form a one-to-one correspondence between the naturals and omega. Simply look at this. We get that we list the natural numbers about like here. But we can also draw the matchstick representation in a one-to-one correspondence. One of the nice things about ordinal numbers is that because they're sets themselves, we can find the cardinality of ordinal numbers. Obviously, the cardinality of omega is going to be omega because omega is the smallest ordinal which can form a one-to-one correspondence with omega. What's less obvious is that the cardinality of omega plus 1 is also omega. And so we can actually think about it like this. The matchstick representation of omega plus 1 is the matchstick of omega plus an extra matchstick. We can actually shift this matchstick back over to the front, which would give us 1 plus omega, which if you think about it, is just, if you concatenate those two together, you just get the ordered set, which represents omega. We've taken omega plus 1, and we've actually shifted it over, the 1 over, so that it's 1 plus omega. And changing the order of the plus 1 actually matters quite a lot, because if the 1 is in front, the ordinal simplifies into just omega. And so we have a similar thing for omega plus 2, like omega plus 2, omega plus 3, omega plus 4. They all have the cardinality of omega. If we try to go a little bit higher, say omega times 2, the cardinality of omega times 2 is actually just omega. Omega times 2, it's like having two sets of ordinals, just like this. Now, what we can do is we can interlace those two infinite sequences one over the other. So we would have 0 followed by omega, followed by 1, followed by omega plus 1, followed by 2, omega plus 2, and so on, which is really just the ordered set of matchsticks 0, 1, 2, 3, and so on. That's just omega. This first thing that we did was like omega times 2. And the second thing, this rearrangement transformed it into something more like 2 times omega. We start with omega and replace each matchstick in omega with 2 matchsticks. And that's exactly what we have in this uppercase. Right? Each matchstick gets replaced by a pair of 0 and omega and so on and so forth, which is really just omega. And this is actually the same for omega times 3 and so on and so forth. Even something like omega times omega has cardinality omega. If you recall our discussion from the last video, that the naturals crossed with the naturals has the same cardinality of the naturals. We use the same argument, and basically naturals is like omega, so omega times omega is just the same cardinality as omega. And so now if we look at our ground timeline of our matchsticks representations, if we look at the cardinality, all of these numbers that we have here that we can construct through addition and multiplication, all of these numbers have cardinality omega. Of course, we do know that there are numbers which look with larger cardinalities than omega. If you remember from the previous video, the power set of n is one example, or you could have 2 to the n, or there are other ways of representing this, like 2 to the omega, or even omega to the omega, and so on and so forth. So later down on this number line, there are ordinals with larger cardinalities, but we just can't see it yet. We don't have the operations to do it. So now that we know the relationship between ordinals and cardinals, how can we use ordinals as a new tool for us to discover things about cardinality? Here's one of them. Remember, originally, our original proof of omega crossed with omega, having the cardinality of omega, consisted of deriving a bijection from omega crossed with omega to omega. However, there is a completely different way that we can go around this by using ordinal numbers. The first thing I want to recall is what is the set omega crossed with omega? What does it actually represent? Omega crossed with omega consists of pairs of elements of omega, namely the natural numbers. So it consists of ordered pairs like 0, 0, or 1, 0, or 2, 0, or 0, 1, and so on and so forth. So what we're going to do is we're going to order each ordered pair AB into a line by this. Order it by whichever has the maximum of A or B, then order it by A, and if you still can't decide it, then order it by whoever has the largest B. So this ordering would look like this. The first element would be 0, 0. It has the smallest A, B, or maximum of A or B. The second element would be 0, 1. That's the next highest maximum of A or B that you could get, the smallest A that you could get, and the largest B that you could get. The second element would be 1, 0. The third element would be 1, 1. The fourth element would be 0, 2, and so on. And you can see this ordering, it will eventually order all of omega crossed with omega. And the great thing about this ordering is that we can actually label all the elements of omega crossed with omega in some order. We could label the first element 0, the second element 1, the third element 2, and so on. And if you notice, if we keep labeling things like this, it looks like they will form an ordinal number. And that's exactly what we've done. It happens that if you have an ordered set with a minimum element, that's what we call a well-ordered set. It can be labeled with some ordinal number, which we call the order type of the set. It's normally denoted OTP of whatever set you have. So in this case, the labels will form an ordinal number, which represents the order type of omega crossed with omega, given this ordering. And we can actually see the order of the elements that we labeled them in on the graph over here. So 0 would go to the first one here, 1 would go here, 2, 3, 4, 5, 6, 7, and then eventually 8 would be here with 2, 2, and so on. And you can see that there's this pattern of labeling, which we form these like bigger and bigger squares. That will be important later. Anyhow, the next step is we're going to try to form an order isomorphism from omega crossed with omega to omega. If we recall this order isomorphism business, it's pairing up the elements of each set one to one, left to right in order. There definitely has to be some order isomorphism. The question is, what does it look like? We have two cases here. The first one is that all elements of the order type omega crossed with omega are paired through the order isomorphism. If that does happen, then we can think about it like this. We can think about the order type of omega crossed with omega being paired with all of omega, and then omega might actually be bigger. So this would imply that the order type of omega crossed with omega is less than or equal to omega in terms of ordinal numbers. So now we can take the cardinality of both sides. And so if you think about it, the cardinality of the order type of omega crossed with omega, it is actually the same as the cardinality of omega crossed with omega, because the order type, the way the order type was created, it was simply just labeling the elements of omega crossed with omega. The order type is in a one-to-one correspondence with omega crossed with omega. On the other side, we have the cardinality of omega, which is simply omega. Therefore, we would conclude from here that omega crossed with omega is less than or equal to omega. Now, the other thing that we know is that omega crossed with omega is definitely larger than omega. I mean, look, it's an infinite set. It's going to be at least the size of omega. Combining these two, we have one conclusion, that omega crossed with omega indeed has cardinality omega. The second case that could happen when we form an order isomorphism is that not all elements of the order type was paired by the order isomorphism. Okay, so suppose we did have an order isomorphism and it didn't end up using all of the order type of omega crossed with omega. So that means there's some ordinal number here whose initial segment does get paired with omega. Now remember that the order type itself is actually in an order isomorphism with omega crossed with omega. So this element that wasn't used has to be associated with some pair AB in omega crossed with omega. So now when we look on the graph, we can plot this A comma B. Now remember that the way we ordered the elements in omega crossed with omega is that they're always bounded by this squarish box. And so this thing about this point AB is that we know that there's no pair greater than AB that can be paired through the isomorphism. So therefore, AB, it defines a boxed region that contains all of the elements that are paired through the order isomorphism. And so this box ends up having a length of whatever the maximum value of A comma B is, so the max of AB. Now let's call this maximum of AB epsilon. Okay, and so here's what we know about epsilon. Epsilon, it's gotta be a finite number. So this region of epsilon by epsilon ordered pairs, it has to be finite. And because epsilon crossed with epsilon is finite, we know that the number of elements paired through the order isomorphism is finite. This would mean that not all the elements of omega were paired, because at some point the order isomorphism would have to stop because it's finite. And in this case, this wouldn't be an invalid order isomorphism because we have to pair as much as possible. So what we conclude from here is a contradiction that comes up because if not all of the order type of omega crossed with omega is used, a point AB, which is an upper bound, is identified for which you can find the upper bound of the number of elements that are paired, for which we derive a contradiction by saying that that region is finite. So it's the case that this second example cannot be. If the second example doesn't happen, then it must be that all elements of the order type omega crossed with omega have been paired. And by our reasoning, it is the case that omega crossed with omega has cardinality omega. So we can see here that what we've used is this sort of indirect reasoning with ordinal numbers. We found a way to order omega crossed with omega, and we reasoned about how an order isomorphism between that order type and omega, we reasoned about how it would look like. And in the end, we were able to determine that the order type is less than or equal to omega. And therefore, omega crossed with omega is omega. And like I said, the nice thing about ordinal numbers is that we can actually generalize this to any infinite cardinal number. For any infinite cardinal kappa, the cardinality of kappa crossed with kappa is just kappa itself, which is pretty amazing. But the argument is actually completely synonymous, except we have the help of our little friend called Transfinite Induction. So to start this off, let's fix K. And for the sake of induction, assume that we've already proved for all infinite cardinals less than that, the equation holds. Assume for all cardinals lambda, where lambda is infinite but less than kappa, that lambda crossed with lambda is of cardinality lambda. Now we want to show that kappa crossed with kappa has cardinality kappa. And as long as we do this, we fit the formula for transfinite induction, and the statement for any infinite cardinal kappa, it becomes true. Okay, so let's try to do it. So the first thing we're going to do is we're going to order kappa crossed with kappa just the same way we did before. So if you recall how the ordering worked, it you start with 0, 0 at the bottom, and then you keep ordering with these squares as you go along. The axes here are kappa and kappa. And so, yeah, we can order it. So we do have an order type of kappa crossed with kappa. Now we suppose that we form an order isomorphism from the order type of kappa crossed with kappa to kappa. Now further suppose that not all of the order type of kappa crossed with kappa has been paired through the order isomorphism. In other words, suppose that there is some pair alpha beta in kappa crossed with kappa such that it's not paired through the order isomorphism. So we can plot this point, let's say alpha beta, somewhere in our graph, and we know by the way that our graph is ordered that this defines some square region for which the elements that have been paired through the order isomorphism exist. And it must have side length of the maximum of alpha and beta. Let the side length of that region be the maximum of alpha or beta. Recognize that because alpha and beta are elements of kappa crossed with kappa, that alpha is less than kappa and beta is less than kappa, which implies that epsilon is less than kappa as well. Therefore, the cardinality of epsilon must be less than the cardinality of kappa. You see, if the cardinality of epsilon was equal to kappa, that would imply that epsilon would actually be the smallest cardinal that bijects to kappa. So kappa wouldn't be a cardinal number. So it must be that this is true. So notice that this corresponds to some cardinal number lambda epsilon. And also recall that the cardinality of any cardinal number is just the cardinal itself. So what we have here is some lambda epsilon that is less than kappa. So recall that this box with side length epsilon contains all of the elements which are paired through the order isomorphism. And so there are a maximum epsilon crossed with epsilon elements in this box. Now, because the cardinality of epsilon is lambda epsilon, there's a very easy bijection from lambda epsilon crossed with lambda epsilon to epsilon crossed with epsilon. Now, there's two cases here. The first case is if lambda epsilon is an infinite cardinal number, then we know that by our assumption here, the cardinality of this is simply equal to lambda epsilon. And remember, lambda epsilon is less than kappa. The second case would be that lambda epsilon is finite. And if it's finite, then lambda epsilon crossed with lambda epsilon is finite, which is less than kappa, obviously. Either way, what we have now is that epsilon crossed with epsilon is less than kappa. This tells us that the number of elements that are paired through the order isomorphism is less than kappa. So this tells us that the order isomorphism not only stops early in the order type of kappa to cross with kappa, but also in kappa. But this simply couldn't occur because the order isomorphism could be able to continue on pairing until one of the sets is gone. It cannot be the case that there are elements left over in both sets. This tells us that our initial supposition that there is some pair alpha beta that is not paired is false. Therefore, all of the order type of kappa crossed with kappa is paired through the order isomorphism. Therefore, the order type of kappa crossed with kappa is less than or equal to kappa. Taking the cardinality of both sides, we know that the order type of kappa crossed with kappa is less than the cardinality of kappa, which we know is kappa. And because it's an easy correspondence from the order type of kappa crossed with kappa to kappa crossed with kappa, we know that this is true. All in all, we have kappa crossed with kappa is less than or equal to kappa. Furthermore, it is quite obvious that kappa crossed with kappa is greater than kappa. Therefore, altogether, we know that the cardinality of kappa crossed with kappa is equal to kappa. Now, following through transfinite induction, we prove that this statement implies that kappa crossed with kappa is equal to kappa. By transfinite induction, we have in fact proved the theorem that for any infinite cardinal number kappa, kappa crossed with kappa has cardinality kappa. So you can see the power in ordinal numbers being able to generalize these statements about cardinality to any cardinal number, which is part of the power of not being required to mention an explicit bijection. Yeah, but let's jump back to something more specific, more down to earth. What I've always found cool about this theorem is that it tells us things like this. The cardinality of the real numbers is the same as the cardinality of the reals crossed with itself, or r squared, and has the same cardinality as r cubed and r to the fourth and whatever, r to the n. This is a really interesting application because it tells us that the number of points on the line is the same as the number of points in the plane, the same as the number of points in space, in 4D space, in 5D space, and so on. So I think that's really cool. And ordinality gives us the perfect tool to solve it. So that's just about it. We've defined numbers as sets, numbers as ordered sets, which are ordinal numbers. We described the relationship between ordinal numbers and cardinal numbers, and I've shown an example about how to use ordinal numbers to prove bigger and better things for cardinal numbers. And there's plenty of other applications in set theory or whenever you're dealing with infinite sets or sequences, which you can actually try it yourself. If you want to try out these exercises, I found them to be extremely applicable to what we learned in discrete math, especially part A, which basically shows that any regular language with a finite alphabet has a countable number of expressions. But yeah, thanks for watching.